Welcome, students, to the final lecture in Organic Chemistry 1. Woo! You'll notice we skipped chapters 12 and 13 because we're not really concerned with the spectroscopy side of things. So we're jumping straight into chapter 14, ethers, epoxides, and thioethers. Ethers, ethers, whatever. So, and some of this stuff we have seen before, some of it we haven't. So we'll go through this. Ethers or ethers or ethers are carbon, oxygen, carbon, and they can be symmetrical, they can be asymmetrical. So you go from water, which is bonded to 2 hydrogens, to an alcohol, which is bonded to 1 carbon and 1 hydrogen, to an ether, which is bonded to 2 carbons. They can be symmetrical, like diethyl ether or tetrahydrofuran, THF. They can be asymmetrical or unsymmetrical, like methylphenyl ether, as you can see here. Right? They can be cyclic. That's a cyclic one. That's a straight line chain. So yeah, it's just a functional group, right? Polarity wise, it is a polar functional group. Okay, oxygen is much more electronegative than carbon, and it causes a point of polarity. So these bonds are polar. However, it has relatively low boiling points, right? So if we compare water, ethanol, and dimethyl ether. So ethanol and dimethyl ether, same molecular weight, right? These are constitutional isomers. Massive difference, almost 100-degree difference in boiling point. Okay, similar dipole moment, right? So the polarity is not all that different. And if you look at the difference, so the difference between water and ethanol is 22 degrees with a 0.2 difference in dipole. So with a 0.4 difference in dipole, you expect a difference of maybe 40 degrees, but no, it's a difference of almost 100 degrees, okay? But it's higher than propane, which is a similar molecular weight, right? So ethers have much lower boiling points than the corresponding alcohol would. And this is because they are only hydrogen bond acceptors. So alcohols and water can hydrogen bond with themselves. They have both acceptor, which is the lone pair on the oxygen, and donors, which is the hydrogen that's attached to the oxygen. But on an ether, right, the carbons cannot act as hydrogen bond donors. The hydrogens on the carbons cannot act as hydrogen bond donors. So you have no hydrogen bonding within a mixture of just ethers. If you mix an ether with something that can do hydrogen bonding, then you will get hydrogen bonding. So ethers have very good solubility with molecules that can do hydrogen bonding. So here's just some common ethers you might run into: dimethyl, ethylmethyl, diethyl, and so on and so forth. And their boiling points, obviously, as you increase the size, your boiling point goes up. Excuse me. So these compounds, ethers, are used as solvents very frequently because they can dissolve both nonpolar and polar substances. So they can dissolve polar substances because you have this big polar part, and then they're nonpolar because they don't do hydrogen bonding. They're not nearly as polar as like water. And also they're unreactive towards strong bases because there's no hydrogen on the oxygen. There's no proton. The oxygen can't get deprotonated because it doesn't have a proton. Okay? And it's really hard to deprotonate just a free methyl group. So ethers can solvate positive ions, so cations, right? So you have a positive ion, all these lone pairs on the oxygens can basically sit around it and solvate it well. It doesn't solvate negative ions because this is, right, lone pairs this is partial negative charge. It's not going to sit around the iodines, okay? So with an ether, it actually lets you solvate, it basically lets you dissolve metal salts, which normally don't dissolve in nonpolar solvents. You can dissolve metal salts in solvents that you wouldn't normally be able to dissolve them in. So there are a couple of times where we've seen ethers complexes. So Grignard reagents, which remember is magnesium and then a halide, usually magnesium bromide, which we use to basically turn this into a very strong nucleophile, right? And you use ethers to stabilize that complex. And same thing with our borane, right? Remember we had diborane with THF, and it forms this BH3 THF complex that we use for the hydroboration reaction. So ethers are really important in terms of stabilizing other compounds. So we also have these complexes called crown ethers. Now don't worry about this naming system. You don't need to worry too much about this. 12 crown 4, 15 crown 5, 18 crown 6 is basically saying that there's 18 carbons arranged in a crown with 6 oxygens. And so 2 carbons between each oxygen. And these are very, very, very good at solvating positively charged cations. So with crown ethers, you can dissolve polar inorganic salts in nonpolar organic solvents. So you might need to dissolve a metal salt into a nonpolar complex or solvent, which normally you can't do, but crown ethers will allow you to do. So common names of ethers, I don't need you to know this necessarily, but you can use this. So feel free to use, and always feel free to use common names, but generally stick with IUPAC because they're A, easier, and B, it's better to be consistent. So you can say it's an ether, right, and then name the 2 things on either side, right? So diethyl ether or ethyl. If you just name one, then you assume that's the same thing on both sides, right? This is tert-butyl and methyl ether. So you can name that in either order, doesn't matter. Tert-butyl methyl or methyl tert-butyl. They say alphabetical order, but I don't care about that. For IUPAC names, you call it an alkoxy group, okay? So here's my biggest carbon chain, 1, 2, 3. So there's my propane. And so that's, doesn't matter which one I start at, 1, 2, 3. So I've got 1 methyl, 2 methoxy, so I've got a methyl group and an oxygen. So 2 methyl, 2 methoxy, propane. Here I've got a cyclohexane, and I've got a methoxy group sitting on it. So for IUPAC, you do methoxy, ethoxy, propoxy, and those sorts of things. Cyclic ethers are heterocycles. So a heterocycle just means it's a ring that has an element that is not carbon in it. So that could be oxygen, could be nitrogen, right? We've looked at that compound as well. So that's a heterocycle. In this case, obviously, since we're talking about ethers, it means that oxygen's part of the ring, but any nitrogen or sulfur, any non-carbon compound that's part of the ring, that is considered a heterocycle. So you have epoxides, which we've looked at. These are also called oxyranes. Oxetane is a cyclobutyl with an oxygen. Furans is an oxalane that has double bonds here. Pyrans have oxanes here. And dioxanes, you don't need to memorize these. Just be aware that you might see these names pop up, and this is what they're referring to. So these are common names. These are not IUPAC names. Oops. So epoxides, you can add oxide, right? Or you can call it epoxy. Okay? So if we have cyclohexene oxide, what it means is instead of having a double bond here, you have an epoxide. But the IUPAC way, which is probably the better way to do it, is you call it epoxy. And you do name both the carbons that it's touching. So 1, 2, epoxy tells me that the oxygen is connected to both carbon 1 and carbon 2. Okay? 2, 3, epoxy. Boom, boom. Right? So this, you have 1, 2, 3, 4, 5, 6. So it's a hexane. You've got 2, 3 epoxy, and you've got a 4 methoxy. And then finally, you can use it as the parent, right? So the base chain you could call oxyrane, right? 1, 2 epoxy ethane in the IUPAC. So you could consider this 2, 2 diethyl, 3 isopropyl oxyrane, but 3, 4 epoxy, 4 ethyl, 2 methyl hexane is probably the way you're going to want to go. I would encourage you to just stick with IUPAC. It'll make things clearer. But the reason we bring up all the other naming things is so when you see them, you don't say, what the hell is an oxyrane? Well, it's an epoxy group. So you can cleave this carbon-oxygen bond to form a carbon-cation, right? But that's not going to happen too much. We've talked about how you form ethers. The Williamson ether synthesis is just an SN2 attack on a primary halide or a tosylate. So you just have the alkoxide, which again, you don't need to show me you forming the alkoxide. You can just have it and the alkyl halide, and then you form an ether. That's the Williamson ether synthesis. So, for example, cyclohexanol and this tosylate, right? You're going to form a bond between this oxygen and this carbon, essentially, because this is going to be this. Well, okay, so this oxygen is going to come in and kick out that tosylate, so that's backwards. But you get the idea. So this is going to become an alkoxide. It's going to attack that methyl group, kick out that iodide, right? And you form an ether. Phenyl ethers are really easy to work with. So in these two cases, right, you have to use sodium or sodium hydride to actually deprotonate this alcohol, because these alcohols are not very acidic. But for a phenyl alcohol, a phenol, they're acidic enough that you can just use sodium hydroxide. Okay, so just that is a strong enough base to deprotonate that alcohol. Okay, you can't use phenyl halides or tosylates. Okay, because they're, so if you had, you can't have that happen. Okay, so you can't use that. So don't just keep in mind the limitations of this synthesis problem. Okay, so if I don't want to make a tert butyl propyl ether, why should I not use Williamson ether synthesis? Well, because this is a tertiary halide. What you're going to remember, you don't get SN2 on tertiary halides, you get eliminations. So you can't do this, you cannot do a Williamson ether synthesis on a tertiary alkyl halide. Okay? So instead you use the sodium tert butoxide, so you put the butoxide on the as the electrophile and have it attack a primary alkyl halide, and that's how you get that synthesis. Okay, you can also form ethers with the alkoxymercuration demercuration reaction. We looked at this when we looked at alkenes, right? So instead of using water to open it up, which gives you an alcohol, you use use any alcohol group, and that'll stick itself on there, and you get an ether. Okay, so if you use methanol, you get a methoxy, and it's always Markovnikov product. And if you use ethanol, then you get an ethoxy. If you use propanol, you get a propoxy, and so on and so forth. Industrially, when they're doing massive amounts, okay, you can actually have a bimolecular condensation. So you take two ethanols and you form diethyl ether. But this is really good for industry, but not great for lab methods. It's really easy to accidentally get an elimination instead of a condensation. So a couple things they make this way: N-propyl ether. If you try to do it with isopropyl alcohol, you don't get any ether. So it's good for forming large amounts of very specific products, but this is not one you want to do in your synthesis. Ethers are generally unreactive, but they can be cleaved by concentrated hydrobromic and hydroiodic acid, with hydroiodic acid being more reactive. And the general mechanism is the alcohol, right, it's a strong acid, the oxygen of the ether gets protonated, and then you get SN2 attack, and then it'll just happen again, right? This ether will then attack another hydrogen, and you get okay, so you end up with, at the end of the day, you end up with two of your alkyl halides, right? So you end up reacting twice. Okay, with aromatic alcohols, doesn't happen, right? You don't generally get that SN2 attack on a phenyl. Okay, so your phenol doesn't do further reaction. So if you have so SN2 reaction cannot occur on sp2 carbon, right? So your phenolic alcohol cannot react. Ethers can also auto-oxidize. So basically in the presence of oxygen, ethers will slowly oxidize and form peroxides. Peroxides are very explosive. They're very dangerous. The stuff you get in the store, the hydrogen peroxide, is mostly water. So it's like a 3% hydrogen peroxide solution. But basically what happens is oxygen over time will just add itself to this carbon to form this hydroperoxide, which can rearrange into this dialkyl peroxide. Okay, peroxide is oxygen, carbon, oxygen, oxygen, carbon. Okay, and these are very dangerous compounds. So you know that if you have ethers sitting around, you have to keep them not quite dry, and make sure you maintain your stock well. That's more of a lab issue. Thioethers, just like thiols are sulfur analogs of alcohols, thioethers are sulfur analogs of ethers. You name the sulfides the same way, except instead of alkoxy, it's alkyl thio. So you could also call it sulfide, right? You can do it the same way. So dimethyl sulfide, methylphenyl sulfide instead of ether. But the IUPAC way you would name this, okay? So you got your 1, 2, 3, 4, 5 pent, okay? The ene, so we got 2-methyl, 2-ene, and then 4-ethyl thio. So thiols and thiolates, same reactions, okay? You can do basically the Williamson ether synthesis using a thiolate instead of an alkoxide. So if you essentially you do the same thing with a thiol that you do with an alkoxide. Hold on a second. All right, bugs in my room. You can do the exact same thing with thiols that you can do with alcohols, essentially. So sulfides can be oxidized very easily into sulfoxides and sulfones. They'll react with alkyl halides to give sulfonium salts. So they are a little more loosey-goosey about what they do than They're a little more loosey-goosey with what they do than alcohols are. So they've got a couple more reactions they can potentially do. So if you treat DMS with sulfoxide, you get dimethyl sulfone to get dimethyl sulfoxide. These are all pretty important reagents, although this one not so much, but dimethyl sulfide and dimethyl sulfoxide are both pretty important reagents. And then, of course, sulfides can just react with alkyl halides that give sulfonium salts, right? So you get that, again, very similar reaction, SN2, but without the cleavage. Thioethers also are excellent reducing agents. We looked at this when we looked at ozonation. Ozonation, the cleavage of an alkene into ketones and aldehydes, right? So you first treat it with ozone to form this crazy ozonide, which we looked at the mechanism for that. And then that gets reduced by sulfur to form, right? It basically scoops up one of those oxygens and you're left with ketone on this side, aldehyde, so 2 carbonyls, and dimethyl sulfoxide. So, yeah, so this is the primary use in the lab is as reducing agents. Silyl ethers, which is a silicon with 3 carbons attached to it and an oxygen. These are used as protecting groups. So if you have multiple reactive functional groups and you want to react one and not react the other, what you have to do is you have to protect one. So what you do, if you were to react with a phenyl Grignard reagent here, right? You could get possibly different reactions, okay? So what you do instead is you react the alcohol with we call TIPS and ammonia, that's also known as TEA, and you get a TIPS protected ether, okay? So you get this crazy silyl group on here, and that prevents any reaction from happening here until you treat it with this butylamine group, right, which then deprotects your alcohol and converts it back into an alcohol. So in other words, your Grignard reagent can react with either your alcohol or your carbonyl. And you want to keep the alcohol and you want to get rid of the carbonyl, well then, right, so since remember, these can just act as acids, it'll deprotonate that instead of reacting with your carbonyl, this is what you want it to do. So what you do is you protect the alcohol group and say, there's no proton here, that's not the oxygen you're looking for. It reacts with the carbonyl, and then you deprotect. The last step you do is you deprotect it and reform the alcohol. So this is a pretty important thing in synthesis. If you have an alcohol, you have something that could react with your alcohol, but you want it to react with something else, you do a protection and then a deprotection at the very end. So sulfonium salts can also alkylate, right? We're hooking carbons together. So if you have a nucleophile, it can attack one of the carbons that's attached to your sulfonium salt and leave you with an alkylation, right? I added a carbon group and a sulfide. Okay, so trimethyl sulfonium iodide, right? Pyridine, here's your nucleophile, attacks the methyl group, and you get methyl pyridinium and dimethyl sulfide. So you end up with it's good as an alkylating agent because you end up with a neutral leaving group. So epoxide synthesis, we covered back in the alkene chapter. You take an alkene, you treat it with MCPPA, which is just a peroxy acid, and you form an epoxide plus a carboxylic acid. You do it in an aprotic acid to prevent the opening of the epoxide. So, right, you got dimethyl cyclohexyl 1,4-diene, boom, boom. And you hit it with one equivalent of MCPPA, and it'll add your epoxy group to the more substituted side. The most electron-rich double bond reacts faster, making selective epoxidation possible. So more things attached here, more electron-rich, so that's going to react first. This one will react second, so if you have a controlled environment, you can actually get selective oxidation there. This is your peroxy acid agent. Don't worry too much about that. You don't need to know the structures. You just need to know the abbreviation to show me that, oh, I'm doing synthesis, I'm doing an epoxidation. Halohydrin cyclization, we've looked at this, right? If you have a halohydrin, you can get the formation of an epoxidation. So it's an internal SN2 attack, right? You get deprotonation of your oxygen. That oxygen then attacks the carbon, which kicks out the halide leaving group to form an epoxide. So you can start with an alkene, do a halohydrination, right, which is just the halogen plus water, and you get the chloronium, right, you get the chlorohydrin, then you put it in base, and you can get epoxidization. Not a great reaction, so the peroxy acid one's probably better. And then, of course, if it's in the presence of an acid, then that acid will protonate the epoxide, and then water will attack the carbon, releasing the epoxide, and you end up with a diol. So when you're doing these reactions, you want to make sure you're not doing it in the presence of an acid, because otherwise you're going to get just opening of the ring and you're going to form a diol. So if you do it in an alcohol solution, right, this is just similar to the alkoxymercuration, right, you can actually get an ether, okay, methoxy, ethoxy, etc., etc. If you do base catalyzed opening, it's a very similar thing, except you end up with nucleophilic attack first instead of the protonation first. But either way, with base catalyzed opening, you still get a diol. So this might be useful if you need to open an epoxide, but you have something else that might be sensitive to an acid. So you can do a base catalyzed opening, and then you just put it in water, and it'll protonate itself. So yeah, so it's pretty easy to open an epoxide because this ring strain gives you significantly lower activation energy. So it's pretty easy to epoxides are pretty reactive. You can also use hydrohalic acid, so hydrochloric acid, hydrobromic acid, and it won't stop at one. So you protonate protonate the oxygen, and then you get SN2 release of the epoxide, and then you protonate the alcohol, and you get SN2 release of the alcohol. So you end up with a dihalide, a vicinal dihalide. So base catalyzed versus acid catalyzed will give you acid catalyzed will if you were, for example, doing now if you're just doing a diol, then it doesn't matter. But if you're, for example, doing a methoxidation, right, where you're adding a methyl group, If you do acid catalyzed, then it ends up on the more substituted carbon. And if you do base catalyzed, it ends up on the less substituted carbon. So that's what you're gonna, right? So if you hit it with ethoxide, right? The base catalyzed, that opens in favor of the less substituted, so the anti-Markovnikov. The Markovnikov is how you can think of it. Okay, predict the major products for the reaction of 1-methyl 1,2-epoxycyclopentane with sodium ethoxide and ethanol. Sorry, H2 and H2SO4, right? So sodium ethoxide, right, you're going to get SN2 attack of the least hindered carbon. So you're going to end up forming the anti-Markovnikov product, for lack of a better term. If you're in acidic conditions, right, you protonate that alcohol, and then your ethanol is going to attack the more substituted side. So you end up getting the Markovnikov product. Okay, so acid-base catalyzed can give you different products. Again, if you're doing a diol, then it doesn't matter. But if you're looking for an alkoxy product, then it might matter. So steroids, the biosynthesis of steroids goes through, so you have this wonky chain called squalene, and it basically goes through some epoxidations that turns them all into turns them all into rings, and then multiple steps, you end up with cholesterol. Cholesterol is the basis for all the steroidal hormones in your body, are all based off of the cholesterol skeletal structure. So epoxides, if you react them with Grignards and organolithiums, which remember are essentially a Grignard are essentially equivalent to a carbanion, and so these will open the epoxide ring by attacking the less hindered side, right? So I've got secondary, primary. It's going to attack the primary carbon and open it up. So you can extend carbon chains this way. So epoxy resins can also be used as a polymer. So you have your epoxide and bisphenol A, BPA, which you may have heard of before. So BPA will form, essentially attack this. It'll attack that. One oxygen will attack that epoxide to open it up. The other will attack here and release that chlorine. So you get this, what they call the prepolymer, and then chain opening, chain opening, chain opening, chain opening. So second epoxide, right? Alkoxide opens up the chain, and then you have, again, just continuing chain. Alkoxide opens. So yeah, it can be used as a polymer. So again, most of these reactions you've seen before. There are a couple of new things to keep an eye on, but mostly this will be useful for your synthesis. So let's look at a couple of problems to start with. Page 678. (14.4). Give the common. Hang on. Give the common when possible. I'm only going to give the systematic. I don't care about common names, so I'm only going to do IUPAC. So give the IUPAC names for the following compounds. Okay. Okay, so I've got 2 carbons here, 1 carbon here, so this is the chain I'm going to start with. Okay, so I'm going to number this 1, 2. Actually, no, I'll just 1, 2. Okay, so I'm working with an ethene. So I'm working with. Now I don't have to say 1, 2 ethene because there's only one possible product, and we'll call it 1-methoxy. Ethene. All right, so we've got a propyl here, 1, 2, 3. And we've got an ethoxy, so we will call this 2-ethoxy propane. Okay, so the longest carbon chain is these two in the middle. Oxygen takes priority over chlorine. Remember, halide has the second lowest priority in the game after hydrogen. So we'll call this 1 and 2. So we're talking about an ethane, and we'll call it 2-chloro, 1-methoxy ethane. All right, so we look at the longest chain, 1, 2, 3, 4, 5, 2, 3, 4. So the longest chain we have is 5. So let's start with 1, 2, 3, 4, 5. Okay, so this is a pentane, and it is a 2,3-methyl. Well, I think methoxy comes first in the alphabet. Yeah, so or ethoxy. So that definitely comes first. So it's a 2-ethoxy, right? 2 carbons off of here, so that's an ethoxy. 2,3-dimethyl pentane. All right, so we clearly have a cyclopentane, and we'll call this 1,1-dimethoxy cyclopentane. Nice. This is a cyclohexane, and it is trans. Well, so now the question is, I actually have to go double check the list whether an alcohol or an ether has higher priority. Actually, need to double check that. I think the list was in chapter 10. Yes. Let's see. Acids, highest, esters, aldehydes, ketones, alcohols, amines, alkenes, alkanes, ethers. Okay, so ethers are second lowest. Cool. So alcohols are way higher than ethers, so we will call this, where am I? There we go. We'll call this carbon 1, and we'll call this carbon 2. So we're going to call this trans, cyclohexane. So we're just going to call this cyclohexanol, and because it's implied that the alcohol's on 1. Trans 2-methoxy cyclohexanol. Right? If we don't number it, it's implied that it's on 1 because it's the highest. So remember, on the rings, a lot of times the highest priority thing will not be named because it's assumed that it's on 1. Or sorry, will not be numbered. Okay. Throw my book away. Come on. Next one. G. All right, so you got methoxy on a cyclopropane. And we don't need to number it because it doesn't matter. However you drew it, it would be on the 1. Okay, H. We have I believe that's correct. Looks good to me. And so, excuse me, alkyne takes precedence over methoxy, but let's see. So we could go 1, 2, 3, 4, or we could go 1, 2, 3, 4. Either way, the alkyne is on 2, so we're actually going to number the methoxy as 1 because that gives everything lower numbers. Okay, so we give the alkyne the lowest number possible. Lowest number possible for the alkyne is 2, regardless of which end we start on. So to give the methoxy the lowest number it can possibly get, we give it the 1. So it's 1 methoxy, but 2 ine. Last one. Double bond here. Methoxy there. Okay, so I'm supposed to start here. 1, 2, 3, 4, 5. So that's a pentene. So it's 2 methoxy, pent 2 ene. Okay, and again, I don't really care about common names. Feel free to use them, but I advise you to just stick with IUPAC. IUPAC is generally easier. The main reason we go over the common names is so that when you see them used, you understand what it's talking about. I don't expect you to use them. All right, next question. Page 683. 14.9. Show how you would create the use Williamson ether synthesis to prepare the following materials: cyclohexyl propyl ether. So we need to obviously we'll draw our reactants or our products over here. So cyclohexyl propyl ether. So we got an ether. On one side we have a propyl. So 1, 2, 3. On the other side we have a cyclohexyl. So what two things do we slap together? Well, I'll do okay, so I've got a propyl halide. 1, 2, 3. Nope, whoop, that's too many. Blah, BR should be here. I got a 1, 2, 3 propyl halide, an alkoxide, ba-bink, and you get ba-boom. Isopropyl methyl ether. So ether, methyl on one side, isopropyl on the other side. So you always want the more hindered part to be the alkoxide. Boom. 1-methoxy 4-nitrobenzene. Okay. So I've got benzene. One methoxy. 1, 2, 3, 4 nitrobenzene. So remember we said that you cannot have a phenyl halide or a phenyl tosylate be attacked by an alkoxide. So we know that we have to start with this guy, and then so for some of these two we could probably switch, which is the right. This could be the alkyl halide, and it'd probably be fine because it's secondary. But for the phenyl, it has to be phenoxide. The ethyl N-propyl ether. 2 ways. Okay, so obviously the two ways are you have ethoxide and propyl or propyl halide, or propoxide and ethyl halide. Okay, both of these work. Remember, you want your halide to be primary. So in this case, since both halides would end up being primary, that's the ideal one. Okay, so although you could technically flip these, this is the more ideal scenario. E, benzyl tert butyl ether. Okay, tert butyl ether. So again, we're given a clue as to what it has to be. You cannot have a tertiary halide for SN2. So we know that this has to be the thing here. So we know we have to have a benzyl, not a phenyl. Phenyl means connected directly to the ring. Benzyl means offset by 1. A benzyl, let's say bromide, and tert butoxide. All right, next question, page 687, 1414. Here. Propose a mechanism for the following reaction. And they drew it in such a way to kind of give you a hint. Okay. Well, we know, and I'm going to draw this. Well, that's fine. We know the first thing that happens is that you get protonation. After which, your bromine can attack. Right? Then that alcohol can get protonated. And then can get, that allows that carbon to attack because water is a good leaving group, which then brings you back to your product. So just remember, when you do an ether cleavage by a halohydric acid, meaning hydrochloric, hydrobromic, hydroiodic, you're always going to get 2 alkyl halides, okay? Not an alkyl halide and an alcohol. All right. Next page. Page 688. 1415. Predict the products of each of the following reactions. We have ethoxy cyclohexane, and hydrobromic acid. So you're going to get essentially stick a bromine here and stick a bromine here, right? So you're going to get water as your product. And then you're going to get bromine there. And you're going to get bromine there. Essentially, you're excising the oxygen and replacing it with 2 bromines. Tetrahydropyran and HI. Tetrahydropyran, huh? I'm going to double check what this compound looks like. I have an idea in my head, but I want to make sure I'm right. Yep. So remember, a pyran is This is why we go over the common name. Propane is like this. Tetrahydro means 4 extra hydrogens, so essentially removing those double bonds. And if you don't know what a compound is, always feel free to look it up. So it's just this with single bonds, okay? Plus, okay, so I'm going to get cleavage here. I'm going to get cleavage here. So I'm going to get, right, let's do it like this. Iodine. Iodine, that's really ugly. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That's what it looks like. C, anisole methoxybenzene. And I think it's offset by 1. Let me double check this. I'm pretty sure that's offset by 1. Nope, that's correct. And hydrobromic acid. Now, again, we're going to get a split here. So we're going to get bromoform, right? But remember, we can't cleave this because it's attached to a benzene. So we're just going to get phenol. D, we have this bad boy. And hydroiodic acid. Again, we're going to cleave here, but we can't cleave there. So that's going to become an OH. So make sure I did that right. 1, 2, 3, and then iodine. 1, 2, 3, and then iodine. Okay, that's right. Again, for ring openings, you can either just draw it like this. You don't have to draw it like this, although it looks prettier like this. You could draw it like that, right? To make sure you have everything in the right place. You can also just number the carbons to make sure you're keeping the number of carbons the same. And E, you have I believe that's correct, or it's close enough as I don't care, plus HBr, so we're going to get cleavage here. We're going to get cleavage here, and we're going to get cleavage here. So what are we going to get? We're going to get 2 carbons here, 1, 2, 3, 4, 5 carbons here, and we're going to get phenol. So sometimes this helps, and this is going to be a dibromo. Okay, so it'll help to just draw them in place. Okay, so we got phenol. We've got our 1 bromo on this side, 1 bromo on that side, and we've got our ethyl bromine. So there you go. And again, numbering the carbons can help immensely if you can't see, oh, I split here, so this is what it looks like after the split. All right. Next question. Page 701, 1426. Show how you would accomplish the following transformations. Some of these examples require more than one step. So we have 2-methylpropene. 1, 2. Becoming that doesn't make sense. Hang on. Two-dimethyl oxyrane. Okay, so here's your 1,2,2-dimethyl oxyrane. So essentially, we've just converted this into an epoxide, and we can do that with just MCPBA. Okay, one step. 1-phenylethanol into 2-phenyloxyrane. Into 2-phenyl oxyrane. Okay. Now this would be 2 steps. So the step 1 is you can just do a dehydration, as phenols are resistant to acid. Okay. And then MCPBA to form that into an epoxide. Okay. Generally, what you're going to want to do is you're going to want to look to form an alkene or something else that can turn into an epoxide. C5-chloropentone into tetrahydropyran. Remember tetrahydropyran? It's like that. 5-chloropentone. Okay. 5-chloropentone is, oh, sorry, that should be our product. And 5-chloropentone, so pentene, so 2, 3, 4, 5. So hopefully you can see we're going to get a ring attachment. So what's going to happen is, first thing we want to do is we want to form an epoxide. Okay, so MCPBA. Okay, and basically what we're going to want to do is we're going to want this ring to open in such a way that it attacks this chlorine and kicks it out to give us that structure. So what can we add that will open that epoxide ring in that way? Well, we can do a base-promoted cyclization of a halohydrin. Okay? So in other words, if we add some base, so this might be a 3-step. So actually, you know what? I don't think we do this. I think we do a anti-Markovnikov addition of an alcohol. So we do hydroboration oxidation. So BH3 THF form, not the what did I do? What did I do? Yikeronis. So transform this into a hydroxy, right? Then that, and then deprotonation. So we'll do 2 steps: deprotonation, and you get base catalyzed cyclization of a halohydrin. I'm going to go to the next page for D. I got room. 5-chloropent-1-ene to 2-methyl tetrahydrofuran. 5-chloropent-1-ene. Okay, so this is the exact same problem. So you got 2, 3, 4, 5 chloro, and we want to form okay, 2-methyl tetrahydrofuran. Yeah, so if we go 1, 2. Yeah, that makes sense. Yes, 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 yes. So instead, we do mercuration, right? Demercuration. Oxymercuration, demercuration. So we use and sodium. No, wait, what was it? Lithium aluminum hydride, or whatever it is, to get to the Markovnikov addition of a hydroxy, and then base catalyzed, so right? Same thing, halohydrogen cyclization, but now we've formed, right? So we add a Markovnikov alcohol here to form this structure. So if we go 1, 2, 3, 4, 5, right? We're connecting 2 and 5. So if we go 1, 2, sorry, we go. Now the methyl should be here. I'm confusing myself. Methyl tetrahydrofuran. Right, we go 1, 2. Something like that. I'm gonna let it go for now. Could be missing a step. 2-chlorohexane 1-ol to 1,2 epoxyhexane. 6, 2-chlorohexane 1-ol. And that, you just hit it with some base. We'll abstract proton. This will attack that and kick out that. Okay, easy. So this one I could revisit and look at, but I'll let you guys figure it out. You can look up the structure and see how you get it, but you definitely get it by adding an alcohol. You may need to shift the double bond over. It might be what's going on there. I have to put more effort into it, and I don't want to do that. That sounds bad. No. All right, you know what? Let's fix this. Okay, so let's see. So 1, 2, 2. So hold on. Methyl 1, 2. Yeah. So okay. Look at the structure of this. My brain's working properly. 2-methyl tetrahydrofuran. Okay, so apparently the okay, I see what's going on. Yeah. So I'm right. It's just the 2-methyl is like this. That's 2-methyl. I don't know how. Maybe this counts as 1, 2, 3, 4, 5. I think you're counting the oxygen in that ring, but the mechanism is absolutely correct. My counting was wrong, so this is correct. I'm correct. Go me. Let's move on. All right, last question we're going to look at is page 705. 1428. Give the expected products of the following reactions. Include a protonation step where necessary. So we've got 2,2-dimethyl oxyrane 2,2-dimethyloxyrane, and isopropyl magnesium bromide. So your Grignard reagent, remember this is essentially like this is going to act as a nucleophile. Okay, so remember nucleophilic attack cannot happen on tertiary areas, so it's going to come in here, open that up. Okay, so you're going to attach, so you got that attachment you just formed here, and bada bing, bada boom. Propylene oxide and N-butyl lithium. One, two, three, four. Yeah, N-butyl lithium. But this time, right, you get attack on the. Let me double check. Yes, I'm correct. You attack the less hindered carbon because it's SN2. You get and then 1, 2, 3, 4. And finally, cyclopentyl oxyrane. And ethyl lithium. Okay, doesn't matter which one it attacks, it's completely irrelevant because it's a symmetrical molecule. So one side will get the OH and one side will get another, oop, that's too many carbons. We'll get another two, woohoo, we'll get another 2 carbons hooked on. There you go. All right, so that'll do it for chapter 14. That's the end. So again, the most important thing for you to remember is when you're thinking about synthesis and you're looking at these reactions, because obviously if it's a one-step thing, you do need to take into consideration, are there possible side products, are there other things that it can react with? So if you have one set of reagents and multiple functional groups it can react with, like acids can react with a lot of different functional groups, what's going to happen. But it's most important for you to think about during synthesis, when you're setting up a synthesis problem, have the conditions I've chosen give me my product that I've drawn and only the product that I've drawn, or is it possible that it could do something else, in which case do I need to use a different set of conditions that do give me the same reaction, or do I need to take a more circuitous route where I do multiple steps, like I have to protect an alcohol, or I need to convert this into this group that won't react with this, and then I can convert it back later. So those are considerations you need to think about when you're doing a synthesis problem. But regardless, good luck on the 4th exam. It'll cover chapters 10, 11, and 14. And obviously, for synthesis, you have access to all of the reactions we've talked about since the beginning of the semester. Well, I hope you've enjoyed Organic Chemistry 1 to the fullest extent that you can enjoy Organic Chemistry 1. Good luck on your exams.